Welcome all. So the second part of the kinetic theory of gases class by myself will start today, and the first one is basically we will discuss here the kinetic molecular theory, which here that it is just the previous part. We will just summarize what we learned from the previous class, that is the particles in an ideal gases. So we already discussed that the ideal gas have no volume and have elastic collisions. That means conservation of kinetic the energy relation will valid, okay, and then are in constant random straight line motion. So here that the schematic representations, you can see here that the molecules are just randomly in motion, but they are in straight line. Next, they are not attract or repel to each other. You can see from their locus or the motion of the air molecule, the gas molecules, the red one, they will just movement, and it is just, we can see that they will not they can collide to each other, but they will not attract. After collisions, they are just scattered in the different directions, right? So, and the last one is the average kinetic energy directly related to the Kelvin temperature, right? So now, to derive the fundamental equation of the kinetic theory, we are considering a cube. That is the gas. Here the gas molecules are basically staying here in this cube. The length, breadth and the height is same, that is we are considering here L. And you can see here that this is the U is the velocity of a particular gas molecule, atoms or molecules, and that these molecules are basically, here it has three components along x, y and z axis, that is denoted by ux, uy and uz respectively, right? And here the capital N number of molecules of ideal gas we are considering here, and each has the mass with m, small m, present in the cube with length per centimeter, right? And then each molecule move in three dimensions, I already told you, and each molecule make one collision when it cut the distance per centimeter. So that means when it is just, we are considering the three dimensions, they will move, but each molecule make one collision when it cut per distance, these things. Okay, so now what is the number of molecules then? The number of molecules, the number of collisions, what is the number of collisions here? You can see that the number of collisions that one molecule make in this direction, that is particular directions that I told you, that is in 1 second, is u1x by L. Why u1x? u1x means in x is the dimension, and u1 is a particular number one gas molecule. Okay, that's why we are just saying the velocity along x directions of this particular number one molecule is u1x, and divided when it will just, before making another collision in between the two collisions, that is we are considering L. So in 1 second, that is the basically number of collisions it can happen, that is u1x by L, right? So this is in 1 second. Now impulse means what? You know that the impulse is basically the force, right? So what is the force before collision? We are just considering, it is just momentum, f u1x, And after collision, what is this? This is basically minus mu1x. Why it is minus m? You can remember that for elastic collisions, I already mentioned these things, that in elastic collisions always there will be the plus, it will just go in the opposite directions. That's why we are considering minus mu1x. Thus the change in the force, that is the impulse, or the change in momentum, which due to collisions with the wall or with the in between two atoms, in the two atoms, then what is this? That is 2 mu1x, right? Because mu1x, it is a vector quantity, so mu1x minus mu1x, because they are going to in opposite direction. So then the force, the difference of the forces, or change in force, that is, we can say change in momentum, better to say change in momentum of this particle, that is 2 mu1x, right? Why I am saying it is change in momentum or the force? Because here the time is in 1 second, so that's why we are saying it is change in momentum or change in force or impulse, right? Now the change in impulse or force in 1 second equal to 2 mu1x into the number of collisions in 1 second. How many collisions was happening or they take place? That is the change in impulse into the number of collisions, that is u1x, that we already derived this part. So we will just multiply these two, then we can get 2 mu1 over u square 1x by L, right? So there is no problems, I think. Now here, that finally the sum of change of molecules of the impulse in all dimensions, we are considering only along x directions. Now for all the directions it will be u square average, bar means it is average, and that is called the root mean square. We can say it is we can say it is square, you know, that first we will mean square speed. This is called the mean square speed. Why it is called the mean square speed? First what we did, that first we take the square of these particular things, and then there will be we have to take the average. So it is called the mean square speed of one molecule, and it's the exerted force by all molecules in all dimensions is basically coming with what is the things, that the 2 m small m capital N u bar square by L. So why we are taking u square bar? That is root. This is basically mean square speed. Mean square speed means we have to square the u1, u2, u3 up to un. Then we will take the square of this and divided by n. That's why it is called the mean square speed, right? And what is the n? N is basically the number of molecules, the sum of change in molecules. That is already we deduct in the previous part. You can check it. That is 2 small m u1 square x L. Now we are considering in only, in the all directions, right, in 1 second. So that's why we are considering u square means that is u1 square, u2 square, u3 means 1, 2, 3 up to n number of molecules are there. So here into n, just we multiply with n, then it will come to with n number of molecules, the sum of change of molecules, that is n number of molecules has this type of the impulse, right? So we are basically finding the force or the impulse, that is we just make these equations 2 small m, you can see 2 small m in u square bar by L, right, in all dimensions. Now the pressure. What is the pressure? We know the force per unit area. So what is the unit area? We know that for a cube the surface area is 6 into the length square. So that is 6L square. So we can just get it, P is equal to F by 6L square. We already find out F in our previous slides, we already showed you. So this into 6. So ultimately this is 2 small m. M is the mass of each gas particles, and how many particles are there? Number of particles is n, capital N, and then U square bar by 6L cube, right? So L cube is the volume of that molecules. So now what is the things? 2 and 6 will cancel out, so we will get 1 by 3, right? 1/3 m in U square by V. So ultimately this is PV is equal to 1/3 small m capital N U square bar. Now U square bar means the mean square speed, right? This is mean square speed, and this is number of gas molecules present in the container, and this one is the mass of each molecule, right? So that will be is equal to PV. This equation is known as the fundamental equation of the kinetic theory. Okay, so that is basically the fundamental equations of kinetic theory. Now here the derivations of kinetic energy based on temperature. Now I am coming to the new one, that is this is a fundamental equations we got. So what is the, you can just write, this is the PV is equal to 1/3 m capital N U square bar, right? Now here the we are going to kinetic energy. What we know, the postulates we already considered in the kinetic theory of gases, that the kinetic theory, the kinetic energy is directly proportional to the temperature in Kelvin, right? So Ke, the kinetic energy, is equal to constant into T, because the constant means the proportionality constant. Now half, this is half mu square. U square means the mean square speed, so half mu square is equal to kinetic energy, because this is a kinetic energy, average kinetic energy, that's why we are saying it is kinetic energy bar. So average kinetic energy is equal to this value into is equal to constant into T. From the fundamental equation of the kinetic theory, what we can write, PV is equal to 1/3 small m capital N U square bar, right? So now, which we are getting from the previous slide. So now we are just putting here 1/3, so the 3 PV by capital N is equal to mu square, right? So we have to put it in such a way like we can get it half mu square, such that we can put this, instead of half mu square, U bar square is equal to constant into T. So now we are writing like this, that 3 PV by small n and Ne. What is this small n and Ne? Small n means the number of molecules in molar. So Na is the Avogadro's number, that is 6.023 into 10 to the power 23. Okay, so capital N, we can write capital N in these terms, that is the number of molecules in the molar sense into the Avogadro's number. Then we can write this. So ultimately, if we will write this, then after that half mu bar square is equal to 3/2 n capital Na, that is Avogadro's number, and PV, right? So now this PV by n, small n is the number of molecules in the molar sense, and into 3/2 Na is equal to half mu square. Now we can write half mu square, instead of half mu U bar square, we can write the constant into T, because we, from the previous slide it was showing there, right? So if we write this, then after that we can get the PV by small n is equal to constant into T. So this constant is basically saying the R. R is basically the constant, means the gas constant, right? That is, we can say the capital R, and that we can, it is a constant, so its values are also constant, that is 8.31, right? So here we are getting the ideal gas equation. This is the ideal gas equation, where you can see the gases, that is the relations are basically given in the, there is a cursor, you can see the PV is equal to nRT. So this PV is equal to nRT means N is the number of moles, that means in the molar sense the number of particles present in the container, the gas container or the gas system, and PV is equal to this. So we are getting the ideal gas equation, PV is equal to nRT. Okay, from this fundamental equation of kinetic theory, what we can write, PV is equal to 1/3 small m capital N u square, that is we already achieved it. So from the ideal gas equation, what we can write, PV is equal to nRT, that we can see in the previous slide, we already prove it. So what we can do, that 1/3 mn u square is equal to nRT, we can write, just we put instead of PV, we can just replace this value. Then what we are getting, that small capital N is basically the number of molecules in this particular gas system, not in the molar sense. When we are saying in the molar sense, then it is a small n. So the capital N by small n is equal to what? Na. We know these things because we are considering this n, capital N and small n both is equal to this is basically Na. Na is the Avogadro's number, that is 6.023 10 to the power 23. Instead of this, we can just put Na, right? So we are getting m into Na into u bar square is equal to 3RT. So what we are getting then, that is basically half m Na u bar square is equal to 3/2 RT. So if we will do it, then what is the things, that here half small m Na u square, that is the kinetic and average kinetic energy into Avogadro's number, that is the kinetic energy. So from there, the kinetic energy of the molecule of 1 mole, kinetic energy of 1 mole, that is, while the kinetic energy bar for 1 molecule, so that is the difference. 1 mole, mole means what? Capital N, again I am just interpret this part, capital N, we are considering the number of molecules present in the gas system, okay, and Na is the Avogadro's number and small n is the number of molecules in molar sense. So that means there is the difference between the kinetic energy and average kinetic energy, right? Now the kinetic energy is equal to 3/2 RT. So the kinetic energy total is equal to 3/2 nRT. nRT, N is the number of molecules in molar sense, right? So this is the things, that 3/2 kT. So here we are considering K. What is K? K is the Boltzmann constant. So what is this value? Value is 1.37 into 10 to the power minus 23 joule per Kelvin, where K is equal to basically R by Na. So it is a constant because R is the gas constant and its value is 8.3. I already told you 8.314 joule per mole per Kelvin, and Na is the 6.022 into 10 to the power 23 per molecule, that is the Avogadro's number. So Na is the Avogadro's number and this is the gas constant. So you are getting the new constant, that is called the Boltzmann constant, that is basically the ratio of the gas constant and Avogadro's number, right? So now what we got the informations, that is, when a gaseous system is in thermal equilibrium, then we can use Maxwell-Boltzmann statistics, and in the Maxwell-Boltzmann statistics, which gives us the probability of particle being in an energy state, and this energy state at a particular temperature. Similarly, what is this? The new another things, that again we can say that reduce the problem to a speed distribution function which is isotropic. Now we are coming to another things, that the Maxwell-Boltzmann statistics, because you know that there is a lots of gas molecules. If the gas molecules are moving in a different directions, after collisions the elastic collisions occur, then we have to use some the probability distribution function. And the probability distribution function is basically guided by the statistical mechanics. So the statistics, there is the classical statistical mechanics is that the Maxwell-Boltzmann statistics, and after that we know there is a Bose-Einstein statistics, and there is the Fermi-Dirac statistics. I am not discussing about this all the things now. So the Maxwell-Boltzmann statistics are basically governing here as the kinetic theory of gases. Here we are considering the gas molecules are always in a random motion, so that's why the velocity directions are uniformly distributed. Also we considered that uniformly distributed, so we can reduce the problem to a speed distribution function. So speed distribution function means we are not considering the velocity, that I earlier also told, that the velocity means the directions are there, direction specific, but when we are considering the the speed distribution, then this will be totally isotropic. Isotropic means it is independent of direction, right? Now there is, let we are considering a v dv be the fractional number of molecules in the speed range. What is the speed range? V and v plus dv. So we are considering this for probability understanding, right? Now a probability distribution function, what is the probability distribution function? That is to satisfy the condition. What is this condition? That what it will basically satisfy, that a probability distribution function has to satisfy the condition. Which conditions? That we should know, that is basically the that to find any particle in a particular space, if we don't know exactly what is the location, then we can say 0 to infinity. Suppose it is 0 to infinity, then a v dv is equal to 1. That means we know that these particles will be present, but it will be coming from 0 to infinity. So we cannot exactly detect the particle's position, but we know that the particle is basically present there, right? So what is this? This is basically the equations which we can write here, that is exactly the 1 by n dn. What is n? N is the number of molecules. I told in the when we started the derivation, at that time we told that n is the number of molecules present in the system, gas system. So it is entire. And what is n? Capital N. Capital N is basically the number of particles. Particles means small n is the number of particles in a molar sense into the Na. Na is the Avogadro's number. Now you see what we are doing here, 1 by n, that means normalization of this, that is dn by du. That means the particles which has the velocity which is moving with the velocity u. So dn by du, it is a normalization. So dn by du, if I will do it, then we can get 4 pi m by twice pi kt 3 by 2 e to the power minus mu square by twice kt u square du. I am not derived this because this is not required to you to derivation. If you are interested, you can ask me, I can send you these things. Okay, so next, what is the, after that, the velocity. What is our main target is here to understand the different types of velocities, like most probable velocity or most probable speed. Better to say speed, because we are considering isotropic. So that's why it is a direction irrespective, and that's why we can say most probable velocity and average velocity, and the another thing is the root mean square velocity. And that we will discuss here, the last things, that is the velocity is in three-dimensional, that is u, ux, uy, uz, that if we will do it, differentiate it, then we can get du, dx, dy, dz. So ultimately it is dq u. And what is dn? dn, I told you already, number of gas molecules that have speed between u and du, u and u plus du. So who are basically moving in this, that is the total number of molecules, and k is the Boltzmann constant, that is r by na. Okay, so and here m small n is basically the mass of the gas molecules, particular gas molecules. So that is the expression. So I am not derive this expression, that if we will consider the probability function, after that we can derive these equations. Okay, so now the distribution of molecular speeds in an ideal gas. So what we will do, that root mean, I told you already, root mean square speed is assumed that all molecules move at the same speed. So what is the difference? Why we are considering the different types of speeds of the gas systems, gas molecule systems? That is, I told you the three considerations. One is the root mean square speed, another is the most probable speed, another is the average speed. So when the molecules are assumed that all molecules move at the same speed, then we are considering root mean square speed. Okay, next, what is this? The motions of the gas molecules is basically distributed. The motion of the gas molecules are basically distributed in the distribution of the molecular speeds in equilibrium. Okay, so it is in the equilibrium. So if we will just say the equilibrium, that means here the statistical, I told you already, the statistical mechanics, if there will be lots of data, generally we are consulting with the statistical mechanics. That means the statistical analysis will help us to understand the behavior of the gas molecules. Okay, so now this is the distribution of different types of gas molecules. The speeds, the different types of speeds means here you can see the red one dotted, and this is basically the Gaussian distribution. So the Gaussian distribution, because of the Maxwell-Boltzmann statistics, we are using the Maxwell-Boltzmann statistics. That's why this is a Gaussian distributions, and the probability and the normalized velocity, if we'll see, then the Maxwell velocity distribution, the red dots is basically saying the, this is a most probable velocity, and this B bar is basically, the green one is basically saying the average velocity, and the VRMS, that is the velocity, root mean square velocity. That means the most of the molecules are moving with this speed. So it is it is not coming in the maximum, maximum molecules are not with this velocity, but it is mostly. Okay, now after that, there are three ways to quantify the typical velocities of distribution of particles in thermal equilibrium. One is, I told you, the most probable velocity. What is the most probable velocity? That is, here you can see that there is a term as most probable velocity. The first typical velocity is the easiest way to calculate. So it is red dotted lines. I told you already that this is the red dotted lines, that means which is the middle one, that will occupy the maximum speed. So this one is called the most probable velocity. So what is the most probable velocity? That is easiest way, as the largest number of molecules have this velocity. And from the velocity distribution, we can see this one, that this is the number of molecules. The probability means number of molecules, the gas molecules which has occupying with this speed. So there it will be the maximum. So it is called the most probable velocity. Okay. So next is average speed. Average speed of a molecule in the gas is actually located a bit to the right of the peak that we have seen. I told you which one. This, the red one is basically the green one is basically the average speed. Okay, here you can see this is given that average speed is basically V bar. Okay, and after that then the blue one is the RMS. So what is the meaning of this? Here we can say that this is basically most probable velocity is the red dotted lines, and the average speed is bit to the right of the peak that I already showed you. The reason of the average speed is basically located to the right of the peak is due to the longer tail on the right side of the Maxwell-Boltzmann distribution graph. So that's why we are seeing it, the average speed, and another is the root mean square. What is the root mean square speed? It is the mean of the squares of the velocities. So mean is just another word like average here. What is mean? So first what we do in this case, first we will take the square, that is a mean square speed. We already did these things during the calculations, derivation of the kinetic theory. The mean square speed, and after that we will take the root. and then it is called the root mean square velocity. So the VRMS we can just simply mathematically we can tell the represented as that the C1 square plus C2 square, that means 1 is basically, you know, this is the molecules, the number of molecules types, the number of molecules 1, 2, 3 up to capital N. So, and first we will do the square and then we will take the average, that is mean, and then after that we will take the root of the same. Then we will say it is root mean square velocity. And then the average speed. So average speed, how we can do this average speed? That is u bar is basically represented by this formula, that 0 to infinity e to the power minus mu square by 2 twice kt u cube d cube. Just the first which we started, we was not derived this formula, we are just using this formula, that is here. And here if we will take a is equal to m2 by 2 kt, so this is just like a constant, so we will take the constant, then we are getting u r is equal to u into dni by n, that is a normalized the probability distribution function. So we are using the probability distribution function, and then 4 pi a by pi, then we will get, if we will do the simple integration, then we will get u r is equal to this value. So after that, if I'll put the value of a, then it will be coming like 8 RT by root under 8 RT by pi m. So you can do these derivations, I already showed you step by step. And now we will do the most probable velocity. Then we have to differentiate, because we know the maximum the number of particles will with the value of u. So that's why the derivative of this, it is a constant. So that's why it is a constant, means if we will take the derivation of this, then we will get 0. So therefore we can get Vp is equal to 2 RT by m. So you can try in your at your own, then you can get the same, no problem. To find the root mean square velocity VRMS, that is we will do this simple calculations, that is kinetic energy bar, that is equal to half mu bar square, so that is 3 by 2 kt. And if I'll just do this u bar square and then take the u bar square is equal to root me the mean square speed, you can remember that I use this term mean square speed. So if I'll take the mean square speed, then mean square speed is equal to 3 kt by m. So if I'll just put these values, then we can get the 3 RT by m. Now we can just put these values, then we can get URMS, that is the expression is root under 3 RT by capital M. So now what is this capital M? Capital M means it is the product of the mass of each molecule into the number of molecules present in the molar volume. So what is the molar volume? The number of molecules present in the molar volume, that is nothing but a Avogadro's number, 6 into 0.23 into 10 to the power 23. So this is basically the root under 3 RT by m. So what we got now, so here we are basically getting the three expression. What is this three expression? That is, one is for, you know, this is this is basically the average velocity. So the average velocity is root under 8 RT by pi m. So you can see all things are constant, only temperature is changing. So the velocity is directly proportional to the root of this temperature, right? So it is directly proportional. So all other terms are basically parameters are constant, right? Now after that we discussed about that the most probable velocity, and most probable velocity we have to take the DFU, that means the probability distribution function with respect to u, because you know that it is a maximum number of molecules are with this, I mean the speed is a maximum in, if you just think about remember the our Maxwell distribution, the probability distribution function, there is a maximum, the Gaussian distribution curve, maximum part was in the there is the df by du. Okay, dfu by du, I mean the fu is the number of molecules with this particular velocity. So that's why we can take, when we take the derivative of this, then it should be 0. So the most probable velocity will be root under 2 RT by m. Here is also we can see that the velocity, the most probable velocity is directly proportional to the root square root of temperature, and the rest of the term are the constant, because you know R and M is a constant, right? Now similarly we did the VRMS, and VRMS is basically the square root of the average speed, and which we can find out easily. In the green part I did the derivation also here, you can just check this, and then we are getting URMS is equal to root under 3 RT by M. So here is also the RMS, the root mean square. So here we are considering the mean square speed, and after that root mean square speed is equal to 3 RT by. So it is also directly proportional to the square root of the temperature. So now we are getting the different expression for most probable velocity, and also the root mean square velocity speed, and also the average speed. Okay, thank you.